new positional encodings just dropped. These ones are called CoPE. Definitely going off the name rope, and that may just be the authors telling us to cope harder because their positional encodings are better. No. So basically, these positional encodings are new positional encodings that look at the context of each token, and according to the context of each token, it creates the position based off that. Thus the name Contextual Positional Encoding, rather than Rotary Positional Encodings, which is, I think, what ROPE stands for, if I'm not mistaken. It's essentially taking ROPE and making it a bit smarter than just counting indices. And that's what the contextual part is. So, real quick, I'll go through normal positional encodings just quickly. So, with the transformer, you have your input. Your input's going to be this sequence here. And the sequence is going to be some tensor that's, we'll call it maybe X. Sure, X works. And it's going to be like an S by D tensor, where S is your sequence length and D is your dimension of each vector. So maybe in this case, this is S equal to 5. And this is D is equal to maybe 512. And each of these represents a part of a word, some word piece. And you then transform this into your queries, keys, and values. So you have your queries, which is going to be S by DK. You have your keys, which is going to be S by DK. And you have your values, which is going to be S by DV. You then calculate your QK, you then do an inner product between your queries and your keys, QKT, and this gives you an S by S matrix. Now this matrix here is going to be where the positional encodings are going to matter, but anyways, you then do softmax along the rows of this matrix, and you then multiply this by the values. And the values are just taking the row distribution and basically taking each vector from that distribution and adding it up. So it's just a linear combination here. Normal attention. The main problem with this is this matrix here doesn't encode position at all. So if we look at this matrix here, we have, maybe it's 5 by 5. I think that's 5 by 5. We have this matrix, and this is the causal case. We don't really care about the bidirectional case that much. So we have this S by S matrix. Now, if we look at this S by S matrix, which is, this is Q, S by D, D by S, So this is going to be the Q dimension, this is going to be the K dimension. Then we have our first output, O1, is just going to be the inner product between Q1 and K1. So it's going to be Q1 and K1. And that's just going to be O1, Q1, K1, essentially. It's going to be a sum. Now here it's going to be a sum of the second query, so Q2, and the first two keys, so K1 and K2. So it'll be an inner product between Q2 transpose and K1, and then Q2 transpose K2. And if you keep on going, let's go to, let's say, this one right here. Q4 transpose K1 plus Q4 transpose K2 plus Q4 transpose K3 plus Q4 transpose K4. Of course, this is not worrying about the values or the softmax, but just to show, just for the sake of argument, to show that the positional encodings are needed, I can simply just say, oh, well, I want to move this position. So, like, this represents position 2, and this represents token 4. So if this represents token 2 and this represents token 4, to me, whenever I'm saying this represents token 2, that's because it's in the second position. But the model doesn't know that because I can simply change the positions around in this sum. And now the fourth, I guess the 2's missing, go back to, oh, well, it's there now. The fourth position and the second position were swapped, but the model doesn't know that. It has the same exact sum. So the positional encodings are not encoded at all in this matrix, and that's why you need to add them. So the way you can add them is, there's 2 ways you can add them. You have absolute positional encodings and relative positional encodings. So absolute positional encodings are basically saying where am I in the sequence relative to the beginning. So in this case here, this vector would just be in position 1, this would be in position 2, 3, 4, and 5. That's really straightforward. The relative positional encodings are also pretty straightforward. It's similar, except like you're obviously still going to do some counting, except it is with respect to the token that is being attended to. So if we go over here to this attention matrix, this represents the first token in the sequence, O1. This represents the second token in the sequence, O2. Here, O2. And this represents the third token in the sequence, O3. And I'm just representing the output as O. So in this case, this would be position 0 because it's, I guess I was using position 1 before. So this would be position 1 along the diagonal, representing the token in the position relative to itself. So it's just the token that's being attended to, and that's just the diagonal. The token being attended to is on the diagonal. Now, if we go over 1 token, then going off the diagonal by 1 is going to have a position of 2 because that is 1 away from the token on the diagonal, and so on. So this will be position 3, this will be position 4, and this will be position 5. And the way you encode this is you can use a rotation. That's what rotary embeddings do, or you can use like sinusoidal embeddings. In the end, it doesn't really matter as long as you're encoding a unique position in a vector form. But these are the 2 ways you can do it. Now, the absolute positional embeddings were the original ones. The relative ones are kind of the newer ones that are used everywhere. And rotary embeddings are slightly better, but they still are terrible at extrapolating. And both are just bad in general at, like, they're bad in general at extrapolating, and they're bad at tasks like counting. Remember that I said each token here does not represent a word, it represents a part of a word. So if you're counting, then it's kind of ambiguous where a word ends. If I have a word like because, that's like quite a long word that maybe a B, cause maybe it takes up 3 positions. But if and that means that a word ends at position 3. Well, if I have a word is, then that ends at position 1. So it's kind of an ambiguous scenario where you don't know how long a word actually is. This is also a problem with sentences. You don't really know how long a sentence is with these embeddings here. So the intuition behind the contextual embeddings is perhaps we can do something like this. If we have the word because that's represented like this, then we can do something like, oh, this is position 0, this is position 0.3, this is position 0.6, or rather, we'll do 0.5 and 1.0. Actually, let me move it over 1. This is position 0, the token before it. Whatever this token is, this will be position 0. And this will be because. So this will be position 0.33, 0.66, and 1.0. So this is the intuition. We can kind of break it up into these smaller positions, so fractional positional encodings. And that's based off the context. So if I had the word is, then this would just be a positional 1.0. So the context tells you what your position is going to be. Now, this is the intuition behind it. Does the model actually learn that? I don't know. Probably not. But what we're basically going to do is have the model learn these positions. And if you make something learnable, it usually does better. So we can see in figure 1 kind of the intuition behind this. So if we have a sentence here, Alice was tired, period. She tried reading, period. A rabbit came. And then it continues. If we look at the relative positional encodings, and we're tending to this last word here. This last word has a position of 0. I had a position of 1 here, but same idea, position 0. And as you go backward in the sequence, the position increases relative to this, because that's how rotary embeddings work, or that's how relative positional embeddings work. Absolute would have this be 0, and this would be 1, 2, 3, 4, 5, and so on. Now, in their case, they basically have this sentence example. So the intuition is they basically want this gating mechanism that's a perfect 0 or 1. In reality, that's not going to happen. So basically it's 0, 0, 0, 0, and then 1 once you reach some certain token, basically saying, okay, we're done with the sentence, move on to the next position. Or, okay, we're done with a word, move on to the next position. That's not how it's going to be done in practice, but that's the intuition behind it. And then it's saying, okay, this is still position 1, still position 1, still position 1. And then the gate fires again, and then it says, okay, now we're at the next position. So that's the idea. So let's check out the method. So the method is down here. I guess we can go through the background as well, kind of where this comes from. So basically they start with this formula here. Where is it? Down here? Yes, right here. So they have this formula. A is going to be some position here. So if we have our matrix like this, so this is going to be our attention matrix. We basically want to add relative positional encodings to it. And the relative positional encodings are going to come from the context. So we're going to work with relative positional encodings, not absolute. Now, these are our queries, and this is going to be indexed by I. These are our keys, and this is going to be indexed by J. And then we have this mask here. Note that the outputs are also indexed by I, so this will be this will be 0, 1, 2, and the outputs are going to be indexed by I. The outputs are indexed by Q. So the formula here, Aij, is equal to the softmax of Qi transpose, and then you have Kj plus Qi transpose E of Pij. Now what this is saying is, this is the normal softmax equation, the normal attention, this part here, normal attention, normal attention for position ij, so one of these positions. This part here is the inner product of the query with some sort of positional embedding, and this here is the position. So this is position 0, 0, 1, 0, 1, 1. It's ij, so whatever position ij is, and this is some vector encoding that position. So what we need to do is we need to calculate this based off the context. Now, I mentioned earlier that they're going to use some gating mechanism. What you can do is you can say, there are a lot of things you can do. You basically want a unique value for each of these, saying how much position does my token add? And that value goes between 0 and 1. Now, I should remind you the sigmoid function, because anything that's between 0 and 1, you just slap a sigmoid on it, and it usually works. Or a gating function, you slap a sigmoid on it, and that's what we do. Or that's what they do. And they mention that you can add a learnable parameter, but like adding a learnable parameter makes this thing like you can't parallelize it as easily, and it becomes intractable to scale as well as normal attention. So what they do is they take each of these values, and they pass it through a gate. That can be seen up here. So we take, that is not an outer product, that is an inner product. I don't know what I was talking about. You take this inner product here between the queries and the keys, and you throw that through a sigmoid value. I hate how the thing keeps popping up. So you take one of these values. This is, say, A00. This is A10. A11. So what you do is you just apply sigmoid to all those. Now, like with normal attention, you apply softmax over here, and you apply softmax on the rows, and we're basically utilizing these values for two things. One is we're going to use this as this gating position, and two is we're going to use these as the normal softmax values. So, yeah, these things, we basically reutilize the attention scores. And like I said, if you wanted to, you could, maybe you throw a projection on the queries and then you do this inner product or something like that. But then that becomes intractable because you have to calculate another attention matrix, and the attention matrix is like the big thing that's annoying to compute. So to make it easy, you just calculate all your attention scores like normal, and you apply a sigmoid to all the values. Now, how do we calculate the position for each of these values? So we want a relative position. We want a position relative to the diagonal, to the token being attended to. And they have that down here. This here is basically saying, so like we calculate the scores, and the scores will be, instead of using A, I'm going to call it, say, what do they have over here? G. So I'm going to call this G because we applied the gating function to all these values. So each of these values are going to be between 0 and 1. So inner product, you apply the sigmoid function, and now we can calculate the values. So the way we're going to calculate these positional embeddings is basically a reversed sum. So this first value here is going to be a sum of itself, and that's going to be the position. So I guess I can write it out down here. So position 00 is just going to be G00. So that's just that one. That's the position for that token there, or for this part of the attention matrix. Position 11 is going to be equal to G11. And then position 10, so for this one here, it's going to be the sum of all the positions to the right of it and itself. So it'll be G11 plus G10. And this is basically just, like, you can think of this as, it could be this, it's basically just counting again, but counting with these fractional values. In the extreme case, if these values were all 1, then it's just normal counting. This is position 1, this is position 2. And if we keep on going, it'll be position 3. But instead, the gates basically allow each token to say, this is just a part. This is a fractional part. It's not an entire part. So it's basically a sum of positions as you go from right to left, or as you go from right to left, or rather left to right, from the original token to the other tokens. We'll do one more. So this is G22. G21, G20. So position 20 would be equal to G20 plus G21 plus G22. So all this. And G21 is just going to be G21 plus G22 for P21. So hopefully that makes sense. Just sum of these fractional values. Now, this gives us a value between 0 and the length of the sequence. So let's say we're at position I in the sequence. Then the position value will be any value. So position I will be a value between 0, if all the gates are 0, and I being the positional value, if all the gates are 1. Now this is probably going to be a value a lot less, but this is a positional value. And in the extreme case, that would be normal positional embeddings. Now the problem is this is a scalar, So how do we convert this to a vector that we can actually take inner product with? Because a scalar only has so much information. It's not scalable if you just use a scalar and just add it. It doesn't encode enough information. So we can just encode this like a normal positional encoding. So encode this to a vector form. Just like we do in rope and just like we do in absolute positional embeddings. Instead of it being 0, 1, 2, and you're assigning a vector each one, we're going to have fractional values like 0, 0.1, 0.25, maybe 0.7, 1.42, 0, something like that. And you're basically going to assign a vector to each one. Now, the problem is these are fractional values, so instead we're going to do an interpolation. We already have values assigned, or we already have vectors assigned to each integer value. So we have a vector assigned to 0, and we have a vector assigned to 1. And we have a vector assigned to 2, until you get to some t, maybe 1024, which is your max sequence length, and you have a vector assigned to that. So we basically have a vector for all these integer values up to some value t, or some max value. I think they call it p max in their case, p max. Now, for each of these positions, we're going to assign an interpolated vector. So if we have 0.5, it's just going to be the vector for 0, or 0.5 times the vector for 0, plus 0.5 times the vector for 1. And E represents the vector. So E is the vector, and this is the position for that vector. So this would be this vector times 0.5 and half of this vector, and you just add it together. So it's just an interpolation. Like if we had, say, 1.1, then the vector that we're going to have is going to be, I think it'll be 1% of this vector, and no, it'll be the opposite way. It'll be 0.9% of this vector and 0.1% of that vector. So for position 1.1, this will be 0.9 times vector at 1 plus 0.1 times the vector at 2. So you can kind of see how this works. Basically, we're assigning it some interpolation between the integer values because we have a vector representation for each integer. And that's basically the method. So we have our formula up here, and you just apply it to everything in here. Now the problem is this becomes disgusting to compute because you basically have a vector for each part here. So a way you can get around that is by pre-computing this part over here. So you basically pre-compute this part and pre-compute this part. And then you don't have to worry about creating this disgusting matrix, 2 of these matrices here. So you pre-compute the positional values. Basically, they pre-compute the positional values with each of the, or they pre-compute the queries with each of the positional values and then just pick them out. Or rather, you pre-compute this right part here, which is this Z, with, so every query that you have in your matrix with every single positional value between 0 and t. So this is all possible positional values. And then you interpolate those. And then you just add it to the softmax of your matrix here. We'll look at the code in a second, and it'll become more clear why they do that. Or how they do that. Yeah. They mention that you can set a maximum value on here that's smaller than t. So t is like the upper bound. T is, or I or t, whatever, the basically your sequence length, that's the upper bound for the positional value. The values are probably going to be a lot less than that, so you can set it to p max to be your maximum value instead of a t value, because each of these values here are probably going to be like 0.2 or 0.5. It's probably not going to be like 1. So you're probably not going to reach the upper bound at all. So I know that they mentioned on like text like a large language model text modeling, they have a t value of 1024. So this is basically saying my, like the amount of tokens I'm sending through is 1024. And Pmax is 64, so the max positional encoding I'm allowing it to be is 64. And they just clamp it to be between, to be less than 64, or to be no greater than 64, the positional embedding. And this way it limits this matrix here, because this matrix here can get big. So let's actually go to the code to see how this is implemented. So basically all we're going to do is pre-calculate these positions. I've kind of annotated it over here. So we have our attention matrix here that we're going to calculate. So self-attention, you have the query, key, and value, and your mask. So first we calculate the attention logits, and you do that by just doing your matrix multiplication, QKT. You normalize it by dividing by the square root. You then apply your masks. This is the mask. I'm not sure why they do log. If y'all know, I don't know. Usually it's a mask with like negative infinity and zeros. I don't know where the log comes from. That may be, yeah, I'm not sure. But they have a log here. But basically this is just your mask. Your normal mask that you're adding to mask the upper triangular. Now, this is the first part over here. That's this part here. We now need the positions, so we have to add these positions to it, the positional encodings, and basically we want to calculate this QT, this inner product with the queries and the positions for every part of our matrix here. So they do that over here, and you want to do that in an efficient way, because this can get quite ugly if you don't do it in an efficient way. So we'll just go through the code line by line. The first part here is you take the sigmoid of all your values in your attention logits. This is just calculating the gate. The second part here is you do a cumulative sum. So this is calculating all the values and storing them in their position. So this first value here is going to be the sum of itself. The second value here is going to be the sum of itself and this value. And then, like, this value here is going to be the sum of itself, this value, and this value. So that's what this flip cum sum -1 flip does. I'm annoyed because I've used this before, and I don't know why they don't have a kernel for this. It should be like simple, because you just reverse the indices in the CUDA kernel launch for this. Not sure. If someone could make a diff for that, that would be awesome. And then you clamp this to the max position. So this is clamping it to Pmax, rather than basically not allowing it to go past a certain position. So like, remember we had T is equal to 1024 and Pmax is equal to 64. So it's not allowing it to go higher than this position here. The cumulative sum. So it's not allowing any of the positions to go greater than that. And that's because you only want to store, whenever we do this multiplication, you don't want to store this massive matrix here. So we then take the lower and upper bounds, because that's how we're going to do our interpolation. So lower bound, upper. This is upper bound, and this is lower bound. I wrote those wrong. Yeah, upper bounds and lower bounds. So these are the integer upper and lower bounds. You then multiply this with the query. Yeah, so you multiply the floating point values with the query. Oh, never mind. No, this is the pre-computation. So this is basically taking the queries and multiplying them with every single positional value. And this basically gives you your positional encodings for each query here. Then this function here it's a gather function. So it's saying on the last dimension, it's basically going to accumulate the values from here and put it into here. So right now we have this integer representation for the seal and the floor, basically saying, oh, this is a value of like 1. This is a value of like 1, maybe on the diagonal. This is a value of 2. Maybe these are 1s here. Maybe this is like another 2, and these are some 2s. Maybe there's some 3s over here or something. So this is an integer value representing the upper bound on the position. These are some floating point values that we're converting, that we converted using the seal function. The gather function is basically taking these values here, or rather taking these values and putting it into here. So this is just accumulating the lower and upper bound values from here. So these were the multiplications, the inner products with the queries, and this is basically just taking so it's converting it from an index to the inner product representation that we have. So these are indices, and these are the basically values pulled from here based off the indices. So that's basically what we're doing there. And then this is doing the interpolation between the lower and upper bounds. This is the upper bound, this is the lower bound, and it's just doing the interpolation between that. So calculate your indices, get the values for each indice, do the interpolation. Then we just add that. We just add that because that's our computation here. And then we do the normal attention after that. So that is how they do that. That's how they do that efficiently. Basically, it's normal rope, but instead of having a step size of 1, you have a dynamic step size. If you know like ODEs, I like to think of it in that sense. You have your normal ODE with a step size of 1. So this is just an straight up ODE with a static step size. I like to think of this as basically having an implicit dynamic step size that the model kind of learns. It kind of learns to take smaller steps instead of just massive steps of 1. So going back up to the top, they mentioned that the complexity is a little higher, but not too much higher, because you don't have the projection. If you have the projection, then it's a lot higher. They mentioned that down here as well. So if we go up here, they mention they have a lot of tasks that they kind of work with. So they have this one here that's like, oh, I have the sequence of like writes and ignores and reads, and we have to end up with this sequence at the end. If you're curious to look at these experiments, they do quite a lot of little experiments, and they show it's like really good at these little experiments that they show, like the flip-flop task, the one up here, where it's like, oh, you write this bit, but you ignore this bit or value, and you read this value. Good old selective copy and counting. An interesting thing about absolute and relative positional encoding is they can't count at all. This one can, apparently. And it outperforms rope by quite a bit. And it does out of distribution tasks better. So they also look at like actual modeling. So, and note that these models are small. I think I don't even know if they're a billion parameters. They're quite small models. I don't remember if they are a billion parameters or not, but I remember these models being quite small, so we haven't seen this actually on scale. But they model this on like actual things you would model this on, wiki text encode, and they show it performs quite well. Here, it performs better than like rope and absolute positional embeddings. Sorry, but it performs a little better than absolute and relative positional embeddings in terms of perplexity. It's not like a ton better, but it's a little better for wiki text encode results. Now down here we have language modeling. So this is where I mentioned they have like a size of 1024 for the window that they use, but they allow the positions to go up to 64. And if we look down here, I feel like this is misleading. So they say that it can generalize to longer context lengths. Now, I kind of disagree with that statement. I could be wrong, But basically, they're saying, oh, we train a model on 1024 context length. And it can go beyond that, which is true, but I feel like it's misleading in a way. Basically, it feels like they're kind of claiming it can extrapolate, but like I feel like it can't. If you have you basically have this model that's being trained on positional encodings from 0 to 64. But like you're training on a context length of, this is basically your embeddings, so 0 to 64. Now, if I train on a sequence length, or if I train on 1024 tokens, so this gives you basically a spectrum, 0 to 64. Now, if I train on 1024 tokens, that can be anywhere between, like the max position can be anywhere between 0 and 64. Now, whenever I'm doing inference, so the likelihood of this being a value of 64 is probably quite small. So let's say whenever they did this example here, the evaluation, let's say at 1024, the positional value at 1024 was, say, like 16 or something like that. Like it's still, like it's not extrapolating the rest. Like if this was position 1024 here, token 1024, like it's not really extrapolating. It's just looking at positions it's seen before. It's just interpolating, essentially. Like, I bet once it gets to token 64, or position 64, it's gonna, like, the perplexity is gonna skyrocket, and it's gonna die, because it's never, like normal positional encodings, it's never seen a position higher than 64. This is essentially just a smart way to interpolate rope embeddings. It's not going to extrapolate well beyond this 64 embedding here. So I would imagine if they kept on going, it would do quite good, and then it would skyrocket as soon as you hit a P max equal to 64, rather than a T equal to whatever it is, because the T is kind of ambiguous. It doesn't tell you what position the model is looking at. It's telling you what position we're looking at. We know this token has a position of 1024. The model knows this position is like 12 or something like that, depending on the gating factors that it had. So it's nice that it can go further with like few positions, but still, like, it's not really extrapolating. It's just interpolating in a smart way. So don't imagine this thing's going to be able to generate infinitely. It's probably going to end up crashing once it gets to a high sequence length. And you can kind of see that over here. It probably hasn't seen these positions very much, and it's already increasing. And these are probably positions like 48 or something like that, something high that it hasn't seen very much. I could be wrong, but that's just my guess, because rope dies really quickly after it hasn't seen this, and this is just a smart way to interpolate rope, where the model learns that. Just something. Don't expect this thing to extrapolate really well. But other than that, it's still like a cool. I still think this is a really cool way to do positional encodings, better than like rope, and better than absolute positional embeddings. But if you're curious, they have more examples showing that this is better than like rope and normal absolute positional encodings. So that is the paper. That is CoPE.